Okay, so in this video, we're going to look at vector components, talk about how to figure them out, why we need them, and if you know your trig functions already, do a little review of trig functions, and if you don't, then I'll be teaching you trig functions. So it bears repeating that a vector is something that has magnitude and direction. A scalar is something that has magnitude only. So magnitude was just a fancy word for like how much, right? So the number value. So a scalar might be something like time or mass, things that it doesn't make sense to have direction to, right? A vector is something where the direction matters. So like things that we're going to end up doing, velocity we've been talking about, acceleration, force is going to be a big one, momentum, stuff like that. So what we're going to do to represent vectors, we're going to use an arrow. So let's say, for instance, I have a velocity of 30 meters per second to the east. Right, I'm in a car going 30 meters per second east. I'm going to represent that with an arrow pointing east and a label of 30 plus my unit, meters per second. So that right there is a representation of everything I need for that vector. 30 meters per second, it shows me the magnitude right here. And then I have an arrow that shows me the direction. So I get all the information without having to write all that mess out. Okay, so why do we need vector components anyway? Well, the answer is because now we're going to start looking at things in 2 dimensions instead of just one. Right? Instead of just northeast, southwest, we're going to start looking at things going at angles. So let's go back to our 30 meter per second vector, except now it's pointing up at an angle, right? So I'm going to draw in my x and y axes, right? Like from math, there's my y and there's my x. So you can see this vector is going at some angle theta from the x-axis, right? We're going to represent angles. The symbol for angles is this Greek letter theta. It's like a 0 with a line through it. So if we want to analyze this, we can't analyze this if it's going across 2 dimensions, right? It's going up. We've been looking at things that just move along the x, and we haven't really talked about just the y-axis, right? But that would be like things that are thrown up or down or things like that are just moving straight up and down, right? We've done this way and we've done this way, but we haven't cut across 2 dimensions. And when you cut across 2 dimensions, you have to break vectors into their corresponding components that correspond with each dimension, right? And it's pretty easy. So if I wanted to draw the 2 vectors that made up that 30 meter per second vector, I'm going to do that in blue. This 30 meters per second vector is made up of a little bit that goes up this way, like this, and a little bit that goes over this way, like this. So you can imagine it's kind of like a triangle, right? If you follow it, then this point meets up over here, and this point meets up over here, right? And what it's basically saying is that this 30 meter per second vector consists of a little bit going here on the x-axis and a little bit going here on the y-axis. So the way we represent those, right, we've been talking about this is a velocity, and that's my vector, 30 meters per second. We represent that by putting a little subscript that says what dimension it's in, right? So this one on the x-axis I would call velocity sub x, and this one on the y-axis I would call the velocity sub y. So my overall velocity is 30 meters per second going, at a 30 whatever angle this is right here, theta, and it consists of an x component going straight along the x-axis plus a y component going straight up and down. Those 2 components make up this one, right? And if you can kind of look, it makes a little triangle, and that's why we're going to start using trig functions to solve for these, and it's really pretty simple. So there's 2 steps to this process, and the first one is actually drawing the components, right? So let's go back to the 30 meters per second. There's 2 ways to do this. I can either start always at the tail right here, and then try to draw two components that will get me over to the head right here. So my two components, I would go in the X direction right here until I'm right below this one, and then I would draw my Y component straight up until I'm directly across from it. That's the way I do it, just because I'm used to doing it that way. If you can see it, then that's an easy way to do it, right? There's also another way to do it. So let's say same 30 meter per second vector. You can still, again, start at the tail of the vector, draw your X component, and then getting to that point, you can draw your Y component straight up, so that this is my velocity, here's my X component, and here's my Y component. And in both cases, it's the same thing. Now later on we're going to get into, it doesn't matter where you draw these because they're always going to be pointing in the same direction, right? So look, see how my X is this long and it's pointed to the right? Same thing. My Y is this long and it's pointed straight up? Same thing. So it doesn't really matter where you put it. However you want to draw it, you can draw it, right? But either way, if it's easier to make a triangle like this, go over and up, that's fine. If it's easier to start and draw over and up like this to try to match to that end point, that's fine. Okay, so here I'll draw three vectors. I'm not even going to label what the values are. I'll just draw them. So there's one there, and there's one like that, and then there's one, let's say like this. So try to picture what those components would look like. Pause it and see if you can picture in your head what they would look like, the X and Y components. Okay, so what they would look like is, again, starting at the tail for each one. This one would look like, I'm going to draw them in red. This one would have an X component like that and a Y component like this. The second one would have an X here and a Y here. And the third one would have a little tiny Y and a big X. And I'll do the other ones in blue just to show you it's the exact same thing. So if I did it the triangle way, it would go over and up. Second one would go over, up. Third one would go over, down. And notice how all of these, the only difference is that, see how over here, this blue one and the red one are on opposite sides? They're still pointing the same direction, right? So over here, the little arrows, they're still pointing straight down. They're still the same size. It's just shifted over, right? And that doesn't matter because vectors, we'll get into later on, vectors can move around all over the place. As long as you don't change the length of the direction, you can move it wherever you want. Okay? So you should be able to just draw an arrow and get the two components. It's just making a triangle, right? You should be able to do that by now. Okay, so the second step to solving these is actually getting the numerical value of the components, right? So we know how much the main vector is, the two-dimensional vector, but we have to figure out how much each component is. So to do that, we got to use our trig functions, which are sine, cosine, and tangent, which you should have learned this if you were in Algebra 2 last year, or maybe they teach you in Algebra 1, I don't know, but they should teach it. If you haven't learned it, then you're going to learn it now. Okay, so if I have a triangle, right, this only works for right triangles, right, it's got to be right triangle, and I have some angle theta. That angle you're measuring, that's the reference point, right? So from that angle, I have a side that's opposite to it, right? So this side over here would be the opposite side from that angle. So I'll call this the opposite side. And this side right here that's next to it, right? So here's my angle, here's the side that's next to it. The side that's next to it is called the adjacent side. Adjacent means next to, right? So I have my opposite side, my adjacent side, and then the top of the right triangle is the hypotenuse. So I've defined these three sides relative to this angle. So if I pick this angle up here, right, that would give me a different opposite and adjacent, because now this side would be opposite, this side would be adjacent. But I'd still have the same hypotenuse. Okay, so sine is going to be the ratio of the opposite side to the hypotenuse. Cosine is going to be the ratio of the adjacent side to the hypotenuse, and the tangent is going to be the ratio of the opposite side over the adjacent side. Right? So all you're doing is you're taking the values for those numbers and dividing them. So if I have, let's say, like a 3, 4, 5 triangle. So here we go. If this is 5 and this is 3 and this is 4, then this is my angle. Then I would say the sine of my angle is opposite, right? Opposite over hypotenuse. So the sine of my angle would be 3/4, and that'll give you a ratio of 3/4. The cosine of that angle would be the adjacent over the hypotenuse, right? So here's theta, that's adjacent hypotenuse. So the cosine of the angle is 4/5. And again, it's just a ratio. So there's a mnemonic device that people use to remember these trig functions, sine, cosine, tangent, what ratios they are. And it's called SOHCAHTOA. SOHCAHTOA. Right? And so all it is, sounds like an Indian guy, right? So sine is opposite over hypotenuse. This is for cosine. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Right? Get it? I guess they still teach that. I don't know. That's the way I learned it in high school, 18 years ago? And I still remember it. So it's just a mnemonic device to help you remember what's what, right? So sine is opposite over hypotenuse, cosine's adjacent over hypotenuse, tangent's opposite over adjacent. And we're mostly going to use sine and cosine. Tangent, like if you get good at it, tangent's something nice to remember. It's not that hard to remember, but we're mostly going to use sine and cosine. Okay, so let's put this all together and we'll solve for the components of a vector. So let's go back to our 30 meter per second velocity vector, and let's say now that it's going at a 30-degree angle from the horizontal. So let's first draw our components, right? So I have an x velocity component going there, and I have a y velocity component going that way. So I'm going to call this my velocity in the x direction, and this one going up I'm going to call my velocity in the y direction. So solving when you know the hypotenuse and the angle is really simple, right? So I'll show you. If I say that, let's start with the x component. So that would be the cosine component, right? Because if I wanted to solve for my x component is adjacent to that angle, right? So the first step, I guess, is identifying which function you're going to use, which one you're going to solve for. So I'm going to pick x, and I know that because x is adjacent to this angle, I'm going to use cosine. Okay, so I know that the cosine of my angle, which is 30 degrees, is equal to my adjacent side over the hypotenuse. So that equals Vx over my hypotenuse, which is 30 meters per second. So to solve, all I have to do is multiply to move 30 over to this side, right? So I can rewrite this as 30 times the cosine of 30 equals velocity in the x direction. And so as a general rule, you can write your equations in that form. So now you're going to take that and put it into your calculator and solve for x velocity. So before you do that, you have to make sure that your calculator is in degrees. So what you do on your calculator, if you have one of the ones from the classroom, you look up at the top and it'll have like a list of the the options at the top, it'll probably say radians, right? Because we've never really messed with this. So to make sure it's in degrees, if it says it's in radians, what you do is you press the mode button. So at the top by the power button, there's a button that says mode. And from there, when you get to that screen, you scroll down a little bit. I think it's like the third or the fourth one. You'll have an option between radians and degrees. And we want to be sure that we're in degrees, not radians. Because if you're in radians and you try taking sines and cosines and everything, it's going to give you numbers based on a unit circle. So like in a unit circle, the sine of 0 is 0, but the cosine of 0 is 1. And then like the sine of 90 is 1, but the cosine of 90 is 0. And it gives you all these weird, it'll give you everything in terms of pi, right? We don't want that. We want degrees. And I don't remember off the top of my head what 30 times the cosine of 30 is. Cosine of 30 is like x over 2 times square root of 2, something like that. Like, do it in your calculator, and you'll get some number. And it should be, I'm going to say between 20 and 30, around there. So let's, I don't have a calculator on me, sorry. So let's do the y component. So my y component is going to be sine, right? Because this one is opposite, right? So if I drew it this way, the triangle way, right? Either way is just as good. See how it's the exact same thing? If I did the triangle way, see how this is opposite? So if I'm going to solve for this side, that's opposite, so I'm going to use sine. So writing my equation, I have sine 30 degrees equals my velocity in the y direction over my hypotenuse, which is 30 meters per second. So again, rearranging, I just multiply to move over the 30. So 30 times the sine of 30 equals my y velocity. And I know sine of 30 off the top of my head is a half, so 30 times a half equals my y velocity, which is 15 meters per second. So let's look at one more, and I'll show you, the real quick process, because right now we can do a lot of generalization. You don't have to write out and solve for every single one like we did that last time, because you're going to be given the value of the vector and the angle. So let's say I'm going to do something like this. We'll go 15 meters per second, and we'll say this is at an angle of 70 degrees, going down that way. So first, draw our components, right? So first component, my y component's going down, my x component is going over. So I'm going to label this Vy, and I'm going to label this Vx. And so now we decide which one we're going to solve for first. So I don't know, I'll pick Vx, right? So my x velocity, again, you might have drawn it like this, right? Makes no difference. My x velocity is the one that's opposite of the angle, right? See how it's not touching? So it's opposite. So that means opposite, I'm going to use sine. So I could, if you want to, like if you like writing everything out, I could write sine of 70 equals my opposite side, which is Vx, over my hypotenuse, which is 15. But in all of these cases, because I'm going to give you the hypotenuse, we're going to know the vector, and we're going to know the angle. If I know those, I can write it in a general form, which is just the value of the vector times the sine or the cosine of the angle, right? So you don't have to write this and then solve every time, because if you know that, I can say that my velocity in the x direction is 15 times the sine of 70, and therefore my velocity in the y direction, which is cosine, right, because that's adjacent to the angle, my velocity in the y direction would be my total vector, my 15 meters per second, times the cosine of 70. And I know a lot. I don't know sine of 70 and cosine of 70 off the top of my head, so you can do those in your calculator. But just knowing both the angle and the value of the vector, I can write it in this form. So any of these ones that you have in the practice I'm going to leave you, you can just multiply the value of the total vector, which in this case was 15, times the sine or the cosine of the angle. Right? So the hardest thing is figuring out, well, it's not even that hard, figuring out which function you're going to use. So if I want to solve for my x velocity component, then I want to use sine because that's opposite. If I want to solve for y, I need to use cosine because that's adjacent. Okay? So, just remember, as a recap, I have a vector, right? Random vector. I'm not even going to give it units. I'm going to call it 50. First, you have to break it into components, right? So, my components in this case would be a y component and an x component, and I could also do it like this, right? Either way is valid. And if I want to solve for, let's say I know this is the angle. If I want to solve for down here, this one is right down here. That's opposite. This one's adjacent. So down here, this one would be 50 times the sine of my angle, and this one over here would be 50 times the cosine of my angle. So all you got to remember, SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. We haven't really talked about tangent, but tangent's opposite over adjacent. Right? So those 3 steps. 1, figure out the components, right? If I have this, make my x component, make my y component. If it's easier to do a triangle, you could go down and over, right? As long as they only stay on the x and y axes. And then second step is decide which one I'm going to use for what. So given the angle, opposite, you use sine, adjacent, you use cosine. And then you plug in your calculator and you make sure that your calculator is in degrees, right? And then you solve.